Next up, we have Patrick Lamb about test suites and program analysis.
Thanks, Yvette. So I'm Patrick Lamb from the University of Waterloo. I'm a faculty member there. Although this year, I'm in Zurich on sabbatical, which is probably the best part of being a faculty member. So I'm doing research in Zurich, and it's great. What I want to do today is I want to talk about another use of test suites. And I want to convince you that test cases can help you with program analysis. So there's going to be 3 parts to this talk. The first part is going to be a brief introduction to what program analysis is and what it can do. The second part is going to be one particular thing that we use program analysis to do on test suites. And the third thing is looking forward what I hope to do research on in the future about using program analysis and test suites together. Traditionally, program analysis came from optimizing compilers where we had programs and we had slow computers, and we wanted to use the compilers to make the program faster. To do that, we really had to understand how the program would work. And so initially, it enabled program transformation and optimization to make it go faster. Program analysis these days can also enable program understanding and other types of transformations like refactoring. It can help to eliminate bugs, and it can help with ensuring software quality. All these things, of course, are similar to things that you might do using tests as well. The observation that I'd like to propose is that programs today come with gobs of tests, and people here have written tons and tons of tests. This is a slide the one slide I recycled from last year. So programs come with lots of tests. We have programs that are hundreds of thousands of lines of code. They also come with hundreds of thousands of lines of code, usually smaller. The hundreds of thousands are smaller, but still lots of lines of code. And another observation I'm going to use is that usually it's easy to understand tests are well structured, and there's extensive library support for tests. So examples of frameworks that people use to write tests are JUnit, nUnit, and other unit testing frameworks. I'm not going to talk about things like Selenium tests. I'm just going to talk about tests that are code. These are the easiest for me to work with as a program analysis person. So let's think a bit about what a test does. A test is going to encode 2 useful things that are very useful to me as someone doing program analysis. They're going to encode how tests invoke, how to invoke the system under test, and they also encode what the system should do. We say, you observe the system behavior, you see if it's what you expect. If it is, then you're happy. If it's not, then you complain about it. And so because we get these 2 bits of information, we can leverage this in program analysis. So my research agenda for the future is to leverage test suites in program analysis. And let me talk a bit about program analysis first, because I keep on saying program analysis. But let's say static analysis is when you look at a program at compile time and you say what it does. So compilers do static analysis traditionally, and they look at just the program text, and they try to understand what they can from the program text. Unfortunately, that's very difficult, for instance, because of the halting problem, and also because of things that are unknown at compile time. You load information from the configuration files, and you can't tell what it is unless you have access to configuration files. So you have to make all sorts of approximations about what the program is going to do for your analysis to work. And so people in the program analysis field say their analysis is sound, but it's not really sound. It's soundy, which is like truthiness, soundiness. So it's like it kind of tells you everything that's going on in the program if you accept the assumptions that it's going to make. So that's static analysis, where you look at the program ahead of time, like compilers. The other type of analysis that you can have is dynamic analysis. And the reason I have this picture is that dynamic analysis really drives the program on one particular path or a limited number of paths through the program. So it gives some input. It runs a program. It looks at what the program does on these particular inputs. And you get very good information about what the program is doing exactly on those paths, but you can't generalize that information to other behaviors of the program, right? That's the usual problem with testing. You know that it works on this test case. What does it do on the other test case? Well, who knows? Could do anything. Right? There have been some works that try to combine these analyses. So this is one particular thing. It tries to find crashes in programs by combining dynamic and static analysis. So you run tests, you infer some sort of specification for the program. Then you do a static analysis. It searches for a bug, and it's like, I think that if you run the program with this input, it's going to crash. And then it runs the program again, and it crashes. So there are things that combine static and dynamic analysis approaches as well. I talked about static analysis. I talked about dynamic analysis. You can, of course, use both of them together. Other approaches are Concolic Analysis, where you run the program with some inputs, but you say, I'm going to leave some of these inputs symbolic. So instead of saying 5, I'm going to say x, and I'm going to run the program with that x through the program. And then you can use a solver to find new paths through the program. OK, so that was the first part where I talked about different program analyses. The second part of my talk, I'm going to talk about one particular analysis that I did using test information as a source. This particular work is done with Felix Fang. Divamjen is right in the front row, and he did an earlier version of this work. The idea here is that you find similar test methods that you can then apply refactoring to. This work was presented at Principles and Practices of Programming in Java earlier this year. And so let's tell a story. I typed some thing into Google saying writing a unit test or something like that. And let's say this is Alice, and Alice is writing some code. So Alice is writing a widget class, OK? And let's say that there are classes foo-widget and there are classes bar-widget. Because Alice is programming in a sane way, there's also tests. So there's foo-widget test, and then there's bar-widget test. OK, so that's great. Now Alice's task is to add a new BazWidget, right? So class BazWidget extends widget. Now, because Alice is working in a sane development environment, there's also going to be tests, which Alice is responsible for writing. OK, so now there's no tests, and we want to go to this world where there are tests. And we'll remember that there are tests for foo-widget, and there's tests for bar-widget. And all these things are similar. So how are we going to get these tests for BazWidget? What's going to happen? Copy paste, right? Control-C, Control-V, right? we have all been there. It's a thing that happens. And you can kind of rag about it, but it's not actually that bad. Developers often copy-paste test. Our results show that they often do. And I kind of enjoy doing it, too. I'll speak for myself here. Right? This worked quite well. For instance, JUnit and other unit testing frameworks, they are often quite self-contained. And so you can get away with doing this, and you change just the thing that you want to change. And it works fine. It kind of leads to some technical debt. And this can cause, we can call it test clones. They can become difficult to comprehend and maintain later, especially when you have 3 is kind of OK. But when you have 20 things that are all the same, that is not so good. Right? And there's been work on refactoring tests. So there's this big 800-page book by Gerald Mezaros about refactoring tests. And if you do that, then you can reduce long-term maintenance costs. You can reduce brittleness and improve ease of understanding of tests. And if you parameterize your test, then it's easy to add on new tests just by changing the parameters, adding new parameters to it as well. And how do we do this at the language level? This is not the work I'm talking about today. This is something you could do in the future. You could use inheritance. You could use method calls. And you could use generics. I will show an example of how we might do this. There's also extensions to testing frameworks where you can parameterize the tests as well. And so let's look at an example of refactoring a test. So here we have some methods. I believe that they're pulled from the Weka machine learning framework. And so there's 2 tests. They look really similar. One of the tests says test nominal filtering. And what it does is it calls this method getFilter, attribute nominal. This other method is called test string filtering, and it's going to call getFilter with attribute.string. And the assertion then is that the result is not nominal, or the result is not string. And so what you do if you want to refactor this is you can say, look, I'm going to set up this array of types. That's one way you can do it. There are other ways, of course. And in fact, in the original code, there's 4 different things. And we can put them all there. And then you can have one test that iterates through all the tests and does the test. So you can argue that this is a better design for your test. It's certainly easier to add new tests. You don't have to use Control-C, Control-V as much. The contributions in this part of the talk are the technique for detecting test refactoring candidates. Right now, we detect them. It's your responsibility to use this information to refactor the tests. And we have an analysis of results on some Java benchmarks. So let's think a bit about what test cases are made of. And so if you have a test case, usually what you have is you have 4 phases. You have a setup phase, a phase where you run the system under test. Then you check that you got what you wanted to from the system. And then you tear down the test infrastructure that you created in the setup phase. In this work, we're going to focus on the verify stage. So we're just going to identify similar test methods by looking at the verify stage and saying that test methods are similar if they have similar verify parts or phases. And the insight here is that if a test is similar to another test, then it's probably also going to have similar asserts. And so the verify phases are going to give you a good idea of when tests are similar. And as an example, I put up 2 tests, and they have similar sets of asserts because we have 3 asserts here. The first 2 asserts are assert equal, one on int and int, one on float and float, and a simple assert true. And so this is going to be the basis of our assertion fingerprints. So in particular, we're going to collect the ordered set of assertions. So you take a test method, and you look at all of the assertions in the test method based on the order of statements in that method. And we're going to collect the assertions along with the parameter types. So we had int, and float, that they were equal. And we're also going to collect some control flow information. So we don't just want the straight order of the assertions in the method. We also want to know how they interact with the control flow, how they are with branches, how they are with loops, and things like that. And I'll talk about that in the next few minutes. And so what we do with that information is we've categorized these methods and collected their assertion fingerprints, and then we group together methods that have the same assertion fingerprints. And I've schematically represented this here with these colored boxes, and we can see that we have some boxes with 4 assertions, and we have some circles with 3 assertions. We say that the 3 circles are in one set of similar methods, and the 2 boxes are in another set, and the diamond is all by itself. So we're going to say these are going to be similar test methods. You should probably look at them to see if they're refactorable. We also collect some control flow components. So there's a bunch of different information that we use to look at the assertions and further classify them. So I'm going to briefly show some test code. So this is just some contrived code, which is going to illustrate how these assertions are in the control flow. And this is a control flow graph where you have the nodes being the statements in the method. You have the edges being the control flow of the method. And we can look at how these do. So what we have is we have these assertions, and we want to talk about how these assertions relate to the control flow of the method. And so I'm going to tell you some intuition about our method. And so there's 5 properties that we use to look at each of the assertions. And we want to differentiate statements, assertions that kind of behave differently. So if you have one statement that executes unconditionally, it executes all the time in a method, and you have another statement that executes if some condition is true, these are probably different assertions, and you probably don't want to say that the test methods that have these 2 assertions are the same. So an assertion that's inside an if statement is likely to be different from an assertion that's not in a if statement. And here on this picture, we can see that we have some branches, and so you can identify, for instance, the blue box at line 5 is an example of a statement that has a branch count of 1. And we keep that information with each assertion to classify it in the assertion fingerprint. There's a definition of it, which I'm not going to go into. Dually to the branch condition, we also keep track of the merges. So we care not only about how many times the control flow branches before it reaches an assertion, but how many times the control flow comes back together before it reaches each particular assertion. And that's another property that we just use. We count these for every assertion, and then we use that to classify the assertions as well. What it ends up being is that for each assertion, we have this 5 tuple. It says, we keep the branch count, we keep the merge count, and we keep the 3 other things. And then 2 method assertion fingerprints are the same if they have the same assertions and the same assertion fingerprints for each assertion. Right, there's a definition of merge count, which I also will not go into. So branches, merges, and the other important control flow information is loops, right? So we saw some test methods that have loops, and some test methods do have loops. So we want to treat differently the assertions that are inside loops from the assertions that are not inside loops. So that's another thing we track. We just keep track of it at the level of a simple flag, whether an assertion is in a loop or if it's not in a loop. And so we did have an example here. So we have a loop that's going from the top up and around. And so we would mark all of the assertions inside the loop as being in the loop. In catch block, so we also track whether an assertion is part of exceptional control flow with try catch. And so if it's inside a catch block, it's probably different from when it's not. So that's another piece of information. And so here we put a try block as well. And so we would notice that the purple one in line 10 is going to be in a try block. We're going to mark that as being different from the other assertions because it's in a try. And the other piece we keep is whether or not an assertion is within a catch block. And that turned out to be useful for some of our benchmarks as well. OK. So we compute these assertion fingerprints for all the methods. And we group together all of the methods that have the same assertion fingerprints. Now, for any analysis, any program analysis, you're going to have the problem of potentially having false positives. And so if you return too much stuff, people are going to be like, there's too much stuff. I can't deal with this. I'm just going to throw out the tool. Forget it, right? So what we want to do is we want to get rid of things that are likely to be false positives. And so we have some heuristic filtering criteria. We say that we only report methods that contain some control flow, that contain more than 4 assertions, or have different assertion types. So these are things that we found work well in practice. If you do that, then the results that I'll show you in the next few minutes end up being pretty good, and you can use them to identify potential refactorable test methods. And so we implemented this using the Soot program analysis framework. And so here's how it works. So you have some tests, test A, B, and C, and then you get the control flow graphs, and then you get fingerprints. And here you can see that the fingerprint for A is the same as the fingerprint for C. So we're going to say these two are similar test methods. You should consider refactoring them. B is all by itself in this example, and so there's nothing that you have to do with it. We had some benchmarks. These are the same benchmarks as last year. I really mean to get new benchmarks, and I will do it after this paper. So this is some results. And what you can see here is that we have refactoring candidates between 16% of the test methods for JGraphT and 55% for Joda-Time. That really had a lot of methods that are quite similar, and you really should consider, if you're the developer of Joda-Time, refactoring that method. We also wondered about what our assertion sets or sets of similar methods looked like, whether we would have a lot of sets that were huge, which would be really hard to refactor. You're not going to refactor 50 methods that are all the same. That's just really hard. It would be kind of interesting. But what we found was that we had some sets that are really large, and we had some sets that have a lot of asserts, but no sets that are both large and have a lot of methods. So either you have this set which has 3 asserts and it has a lot of methods, or you have this set that has 40 asserts and it has a couple of methods in it. We also wanted to know how good our results are, so we did some sampling here. What we were trying to find out is, would it actually be reasonable to think about refactoring these? And so there were a lot of results. There's hundreds of results. But what we did was we sampled 20 of the results randomly from each of our benchmarks. And so the blue part, the first part of the bar, is what we call true positives. So in our opinion, all of the methods there could actually conceivably be refactored. It would not be stupid to factor them. The orange part is where you have some methods, some subset of this set of methods, which would make sense to refactor. Perhaps you have 2 different sets of methods that would make sense to refactor in this set. So there's a lot of methods that we return that are actually refactorable. And some of them, the complete set, you all want to refactor into one test. Some of them, there's multiple different things that you would want to refactor into different tests there. We did some qualitative analysis to know how our work would work. And so we found for JGraphT, we had these small and heterogeneous tests which were unlikely to be false positives. So we had these small tests. So they're small, so they're not super worth refactoring. But if you do refactor them, then they're probably good to refactor. Joda-Time had this wide hierarchy of tests. So the thing about Joda-Time is that it's a library for time, keeping track of time. And what you have is you have, for instance, like the Gregorian calendar and then the Coptic calendar, and you have all these things that are pretty similar. And so you can imagine it might make sense to refactor these tests as well. And they have identical structures, and they have straight line assertion, so there's no control flow going on here. You just have assert, 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 assert. And that makes a lot of sense to refactor. So this was actually, in some sense, the easiest thing that you could imagine refactoring. Some other tests had textually identical clones of methods. So it really did look like someone did Control-C, Control-V. This was a thing. It had similar data types, but they ran in different environments. So that's a thing that you'd have to consider when you're refactoring these tests. This one didn't work so well. Google Visualization, it's an old visualization library. What it had here was it built up a query, and then it did a query. It built up the query, and then it said, go ahead and execute that query. And that was pretty hard to refactor. It also had helper methods, which reduced the role of assertions in these methods. So what we found was that there were test methods that had structural similarities, and we think those are really amenable to refactoring. And there are also some non-parameterized or small methods that were difficult to refactor. So the next step that we'd like to do in this particular work is guided test refactoring. So now we've identified things that are likely to be refactorable. So now we'd like to present them to the developer and say, look, we think that you can do this transformation. Is this really a good idea, or is this not a good idea? What do you think? If you think it's a good idea, we can go ahead and do the refactoring for you. And here you have this better test suite. And I think that would be pretty useful as a tool for developers. OK, the final part of my talk is more speculative or forward-looking. And I want to talk about future perspectives about doing static analysis and dynamic analysis using tests as information. Because I think we have this great source of information, and really, we should use it, right? Because we need all the information we can get to do program analysis. And so let's step back here, and let's think, well, what do we usually do with tests? And usually, OK, so you go through a lot of effort to write the tests. And then what do you do? You run the test, and then you get a yes/no answer. We had that great talk yesterday about flaky tests, where sometimes you get this no answer, and you shouldn't ignore it. But in any case, you get the answer, you analyze the answer, and then you see if you have to fix the code or not. You can also combine this with other analyses as well. So let me put this in some pictures. So if we're talking about static analysis, then the usual interaction with tests is you don't interact with them. So you have your program, you have some analysis tool, and you run the analysis tool on the program. You don't look at the test at all. You're like, oh, forget about it. And, well, you get some results about the program. Maybe you're going to generate some tests. But the thing that seems like a shame is that you just generate the tests, and they're just there. You don't look at them at all afterwards. They're just output. So the idea here is that a lot of static analysis work just ignores the tests flat out. And it's like, there's this source of information. Why are we not using it? What's going on here? The usual interaction with tests for dynamic analyses is not quite as grim. So because it's a dynamic analysis, because you're actually running the program, you have to do something to get the program to run. And so you do use the tests as input. And then you run the tests through the program, through the analysis tool, and then you get generated tests. So tests are write-only in some sense. You still generate these tests, but you don't really do anything with them. So what I'd like to look at in the future is that there's got to be some sort of better way. Look, we have these tests, and the analysis tool really should be using these tests as part of the input, as part of the information that it uses to understand what the program does. So it should use both the program and the analysis tool together to better understand the program and do all these wonderful things with the program. Some other insights are, well, why is it hard to write tests? Well, there's a lot of challenges with writing tests. Two of them that I identified here are that you need to get the system under test into an appropriate state, and that's hard. And you also need to decide what the right answer is. That's also hard, and we had some talks. For instance, we had the image talk, and OK, so that's just hard. But you need to have both of these informations to understand what to write the test. And this information is also useful for static analysis. We should just use this information and do better static analysis with it. They also illustrate interesting points in the execution space. So you do random executions. You just don't usually get things very interesting. But you have these human-written tests, and they say, look, somebody thought that we should look at this execution program. It's probably interesting. And they also provide complete execution environments for program fragments. There's also a couple of other challenges as well. So you have multiple test runs. You have zillions of tests, again, as I said. And how do we combine this information? The other thing is, what can we learn from failing tests? What can we learn from flaky tests? There is certainly signal there. How can we better incorporate this into our program analysis tools as well? And so what I think is that there's this great opportunity for using all this information that's provided by developers and testers when developing and testing the program. And all we do with this test now, we just throw that information out. We just generate maybe some more tests. But if we were smart about this, and we can use these tests as a valuable source of information about the programs that they're associated with. Thanks.
Thank you, Patrick. So could you elaborate on the background for choosing 4 as the cutoff number for assertions? 4 sounds like a lot for a scope test.
Seems to work well in practice. That's what I got.
What is the name of the tool you use for program analysis?
OK, so that's the Soot framework. The Soot framework is this open source library that you can use to do program analysis on Java bytecode and source code. And if you do a search for like Soot Java, that should pull it up.
How do you measure the maintenance impact of such refactorings?
That would be future work. Yeah, you'd have to do it, and then you'd have to see if it's a good idea. It might be a bad idea. That's possible too.
In your experience, are developers generally on board with using program analysis tool? Doesn't it create more work for developers when the tool identifies completed test cases that are candidates to be refactored? Would you say program analysis is more or less critical than having a wider coverage of tests?
There's a lot of issues with using program analysis tools. It's hard, right? And it's also hard for me to have a blanket answer for that question. I think that if you design your Coverity is an example of analysis tool that was heavily engineered to really be useful to developers. Even then, it's not always used. But if you really engineer your tool so that everything it tells you is useful, then it is giving you signal that you would want to use. Whether it creates more work for developers, yes and no. It helps you eliminate technical debt, right? And so that costs you time to eliminate technical debt, but maybe it's going to be worth it. That's going to be a judgment call on the developers, for the developer to make. Is it more or less critical than having a wider range of tests? I think these are complementary, and you actually want both. Of course, we live in a world with finite resources, so you can't actually say both. But you can't just ignore one. You can't just ignore the other. It would, crazy languages like JavaScript don't actually have any program analysis at all, like by default. And so that's one end of the spectrum. But I think most people actually like to get compiler errors as opposed to deploying and getting compiler errors. So we have this spectrum, and you can be at different points in the spectrum depending on the type of project that you're working on.
Do you suppose that some of the tests detected as refactorable were originally generated by an algorithm?
We did look at the tests, and in our particular test suites, we didn't have any generated tests. In general, that could well happen. In that case, you would probably want to blacklist this test, and you say, look, don't look at these tests. They're obviously not useful to look at.
And can refactoring tests reduce readability and understanding of what the test is doing?
That is definitely fair. It is a judgment call, so I'm going to hedge here. Sometimes refactoring the tests can lead to better design. Sometimes refactoring tests leads to worse design. And yes, it obscures where the error is coming from. Nothing is always a good idea, right? So look at your particular situation. If it makes sense to refactor, then go ahead and do it. If it doesn't make sense, don't do it.
And that seems to be all. So thank you.
All right, thanks.